very long. Okay, so I'm going to talk about three papers that have come out recently. There's a few more underway, and there's some students involved: Slava Lysov, Prahar Mitra, and Temple He. And in my brief half hour, there are 4 points I want to get across. I'm going to talk about, well, the title is BMS Symmetry and Weinberg's Soft Graviton Theorem. And let me begin by just briefly saying what the points are I'd like to get across. The first is that the BMS transformations, which I will review, are an infinite dimensional set of symmetry transformations of Minkowski space, which were discovered in the early 60s. But they're a symmetry only, they were described only as a symmetry of Scry. And I'm going to argue that BMS is an infinite dimensional symmetry. Well, I'm going to find oh, it's not working? Can everybody hear? Okay.
Sorry.
So I'm going to say that there's a kind of generalization of BMS symmetry, which I'll describe explicitly, which gives us an infinite dimensional symmetry group of the S matrix, or classical gravitational scattering, in four-dimensional Minkowski space. It's a spontaneously broken symmetry. And a second point is that what we call soft gravitons, a word that gets used a lot in scattering theory, that soft gravitons are exactly the Goldstone bosons of this spontaneously broken symmetry. Thirdly, we know that whenever we have a symmetry, there's always a conservation law. And here we have infinitely many symmetries, so we expect infinitely many conservation laws. A global subgroup of this BMS symmetry is just time translations. That gives us global energy conservation. But this infinite dimensional symmetry gives us something which at first sounds rather surprising, which is, in fact, in gravitational scattering, both quantum and classically, that there's energy conservation at every angle. That is, the energy coming in, the total energy coming in from the South Pole always equals the total energy going out at the North Pole. And I know this raises many alarm bells, but it's true. And when you see exactly why it's true, it has to do with the nature of the definition of gravitational energy. You can make up your mind of whether it's a deep new discovery about gravitational systems or whether it's a trivial consequence of the way that energy is defined in general relativity. Finally, there's a ward identity of this symmetry. And the ward identity, oddly enough, was discovered about the same time as the BMS symmetry itself, and it's known as Weinberg's soft graviton theorem. In fact, one could have worked this talk the other way around and derived BMS symmetry from Weinberg's soft graviton theorem. And finally, I can't describe it all in 30 minutes, and I won't mention this much, but everything I'm going to say about gravity is also true both for non-abelian gauge theories with massless gluons or electrodynamics with charged massless particles. There's infinitely many symmetries, asymptotic symmetries. They have a ward identity, and their ward identity is what we call the soft photon or the soft gluon theorem. More generally, what I'm trying to do is forge a concrete link between two kind of lines of investigation that have gone on for the last 50 years. One is sort of scattering in Minkowski space, which is done in the language of Feynman diagrams, and the other is mostly by relativists of studies of asymptotic structures in space-time. And it turns out that these two things, as one might expect, are linked in a very concrete way. And as many of you could guess, my sort of secret motivation for all of this was one wants to understand something about a holographic reformulation of Minkowski space-time. Of course, I don't have that now, but I believe that this is the language that we're going to need to set up such a thing. Okay, so let me start by describing or giving a lightning review of what BMS transformations are. So I'll start with a picture of Scri plus, or the future half of Minkowski space. And it's natural to adopt coordinates, retarded time u, which runs from plus infinity to minus infinity on Scri plus. And then we have a radial coordinate r. And then I'm going to label the spheres at fixed r and u by complex coordinate z. And in these retarded coordinates, the flat Minkowski metric just takes this form. But we're going to be interested more generally in asymptotically flat spacetimes, where there are corrections here. And let me write the two. There are a lot of them, and they take a very complicated form. And there's a rather intricate and highly developed story of how all the subleading terms fit together, which I'm just going to completely gloss over in this talk. But the important ones are, first of all, the one that you're familiar with in Schwarzschild, which takes this form in these coordinates. For Schwarzschild, of course, this would be a constant, the 2m over r correction. But in general, for a general spacetime, it depends on the location in the sphere. And even if you boost Schwarzschild, it's no longer constant. That's one important term. The second important term is a subleading to this term, and this represents.
U and R are both like?
No.
Oh.
No. Lines of constant r look like this. Lines of fixed u and varying r are null, but lines of constant r and varying u are time-like. So if we imagine, say, a graviton coming out here with some transverse polarization, the transverse polarization vector will be tangent to the sphere. And so these are the these terms are very important when you have gravitons going up to Scri plus. And sorry, the bonding mass, of course, can also depend on the retarded time u. And this CZZ, again, depends on ZZ bar u dz squared. These two fields don't depend on r by definition, because I'm doing an expansion about Scri plus. So those are the important terms in the metric. Now, what is the BMS group? Well, the BMS group it's a complicated infinite dimensional group, and I'm just going to kind of give you a cartoon of it. There are two types of generators. One type of generator acts like Lorentz transformations on Scri plus. So this is a picture of Scri plus. It's a vector field. Of course, it's only really the asymptotic part of it that matters, but it's a vector field that looks like this. It's SL2C boosts, Lorentz boosts. Now, by the way, SL2C, of course, is SO31, the Lorentz group. And this sphere at infinity is a conformal sphere. And SL2C is, of course, the global conformal group of the sphere. And the fact that the global conformal group of the sphere, SL2C acts there, means that we can anticipate that there's going to be some kind of conformal structure that's relevant to, on the two-sphere, to any kind of Minkowskian scattering process. Now, the second part, and these are generated by vector fields that look like on this at infinity, like dz, z dz, or z squared dz dz. Now, the more surprising part are the so-called super translations. And now I'm drawing the sphere sitting out here, labeled by z. And the super translations, of course, there's a symmetry which translates everything along scribe plus. That's just d by du. But in fact, the theory on scribe plus is, in a sense, ultra-local. And you can independently translate every point on scribe plus. They don't have to have the same magnitude. So the super translations are generated by f of zz bar du. And BMS argued that if you take that the BMS group is sort of all the allowed diffeomorphisms, that is, all the diffeomorphisms that preserve some boundary condition that they defined very precisely, modulo the trivial diffeomorphisms, ones that do nothing to the physical data at infinity. Now, it's obvious that this is a boost. If you have some physical data at infinity and you boost it, it's obvious that it's a new physical situation. What are these guys doing? Well, this allows you to translate differently. Suppose we have a situation where we have two gravitons which come out at the same value of retarded time. Then we can do a boost, which is 0 on the south pole and non-trivial on the north pole. So we can do a transformation which delays one of the gravitons. So that's clearly different. We'd call that a different situation, where gravitons at different points, you're changing the time at which they come out in an essentially arbitrary way. And BMS argued that these were, roughly speaking, all the non-trivial generators. Now, if we take these super translations and we act with them on this CZZ up here, we find that it's equal to F du CZZ. That is, it translates along scry, which is exactly what we'd expect. But then there's an important second term, which is minus 2 dz squared F, where dz is the covariant derivative compatible with that asymptotic metric on the unit metric on the sphere. So the C's transform inhomogeneously. So we see that it doesn't leave the standard flat Minkowski metric invariant. So the C's are the Goldstone, related to the Goldstone boson. They're kind of derivatives of the Goldstone boson field for broken super translation invariants. OK, now there's a completely parallel story for scry minus. And at scry minus, we have ds squared is equal to minus dv squared plus 2 dv dr. And OK. And so then there's a BMS plus, which acts on scry plus, and a BMS minus, which looks nearly identical, which acts on scry minus. All right. Now, in quantum gravity or in classical gravitational scattering, we want to understand the relationship between in states or in field configurations and out states or out field configurations. In other words, we want to solve the problem out is equal to S matrix on in. And so we want to relate the two. So it's very natural to ask, so we have these two groups, one which acts on out and one which acts on in. And it's very natural to ask whether there's some sense in which they provide a symmetry of the S matrix. And, in other words, is there some operator that commutes with the S matrix related to BMS transformations? To my astonishment, this is not mentioned anywhere in the literature. So BMS was always thought of as a symmetry which acts on the Hilbert space at scry plus, the Hilbert space at scry minus, or the classical data, more likely, at scry plus or scry minus, and it was characterized as something that preserves the symplectic form up there. Now, there was a reason why this question, so I asked why nobody ever thought about this, and the problem is this. If you the answer I got was that there is no way to associate an element of BMS plus with BMS minus. So if you draw a picture of Minkowski space, Penrose diagram of Minkowski space, we have scry plus here, scry minus here, and then we have spatial infinity out here, and then we have something which is slightly different, which I call scry minus plus. It's the future sphere of scry minus and scry plus minus. Now, if you look at the Penrose compactification or the conformal compactification of Minkowski space, we paste it onto the Einstein cylinder. So let's go around the back. This is now I0, this point here, and it goes up like this. This is something we're very familiar with from ADS. And this point is a singular point. This point was well known to be a singular point in the conformal compactification. And so it was thought that it kind of severed scry plus and scry minus, and that there was no way you couldn't write down. So I wanted to write down an equation like, is there some operator? I have to do the middle. OK, so is there an operator of the form B plus S minus SB minus is equal to 0? So you have to know, given a B plus, what you call B minus. And people were worried about all kinds of logarithms and stuff, and it didn't quite work. Then, OK, this was a long time ago. Then there was some really seminal work done much later by Christodoulou and Kleinerman in the 90s, in which they really, a beautiful work in which, very important work in mathematics. Physicists haven't heard about it so much, but it's a central development in differential geometry, in which they really understood finally the structure of Minkowski space, how everything falls off at scry plus and scry minus for data in a neighborhood, and they proved rigorously the stability of flat space and so on. It was beautiful work. And I didn't need to understand much of that, fortunately, because I couldn't. But it turns out that for these Christodoulou-Kleinerman spacetimes, which represent a finite neighborhood of flat space, it's just smooth enough that you can nicely tie scry plus to scry minus. And that was kind of what was getting in the way earlier. And so I'm just going to tell you what the result is of the canonical way to tie scri plus to scri minus, and I'm not going to derive it, but it's essentially fixed by Lorentz invariance. The first thing, what?
Are you saying that their condition is stronger than asymptotic flatness?
Well, there are 1,000 different versions of asymptotic flatness.
But than any of the ones that we would have used?
Not than any of the ones that we would have used. And the important thing was whether if you have smooth additional data, whether you get logarithms as you go back here. And anyway.
So in particular, can we consider most of the solutions that we know and like in this setting? So, I mean, it doesn't include partial black holes.
Oh, sorry. So I am now talking, there should be a story with black holes, but I'm really now talking about weakly gravitating systems that begin and end in the vacuum. And Christodoulou and Kleinerman are certainly all specifically below the threshold of black hole formation. Well, I don't want to say their work wasn't perturbative, but yes, it's a neighborhood. It's below. Don't think about black holes. It's a finite neighborhood of flat space. Okay, so and what you want to do is, if I call the identification that you want to make, now there's a funny antipodal map that comes in. Because you see, Lorentz transformations are not, if you look at what a Lorentz transformation does on I plus minus at the North Pole, it's not the same as what it does at I minus plus at the North Pole, right? Because if you're boosting towards something on scri plus, you're boosting away from it on scri minus. So the identification involves, just for Lorentz invariance, even for this Lorentz subgroup. So obviously we all know that we can get one symmetry of the S matrix by identifying the Lorentz subgroup of scri plus with that of scri minus. And for that, we need to use, you don't identify a point here with a point here. You identify a point here with its antipodal map here. And that looks more natural on this diagram, where you say that things should be smooth on these null generators of scri in the conformal compactification. So then the boundary conditions are the simplest thing you could imagine, which is that MB, the Bondi mass aspect, which depends on Z and Z bar, evaluated at scri plus minus, is equal to MB at scri minus plus, where by the same point, I mean in the sense of along the null generators. And moreover, the super translations F, let me call them F plus for the ones on scri plus, ZZ bar have to equal F minus ZZ bar. So the super translations are constant along the whole null generators. It's the simplest thing you could imagine, and it's the only thing that is consistent with Lorentz invariance. So now we've learned something about classical gravitational scattering. If we set it up in this way, that is, we know that if we have some incoming gravitational wave goes to Mount gravitational, we can boost the initial data, and that will scatter into the boosted final data. But from the super translations, we're learning something much weirder, right? So suppose we have some situation where, we can boost all the incoming, we can delay all the incoming stuff on the South Pole, and by doing a BMS super translation, and without solving the bulk equations again, if we're given one solution, we can get another one which has a delay in the outgoing data near the North Pole. So this is a new symmetry of gravitational scattering. Now, let me say something about energy conservation. No, f of z, so f of z is just an arbitrary function on the sphere which parameterizes the symmetries. I mean, I've assumed whatever BMS and Christodoulou. Well, okay. So, I mean, strictly speaking, I've assumed everything that Christodoulou assumed, which is the Einstein equation. Okay, Christodoulou talks about the Einstein equation, but in the end, this whole story is going to be equivalent to Weinberg's soft graviton theorem, and so it's very likely that it's, you know, an exact symmetry of any theory of quantum gravity coupled to matter. What? No, it's very specific to 4 dimensions. Okay, so now I want to talk about the constraint equation. So the constraint equation tells us that the time derivative, the retarded time derivative, so as we move along here, this would be u, that the change in the Bondi mass aspect, which depends on z, z bar, and u, has 2 contributions. The first is minus what I'm going to call TUU. And TUU, if we had a scalar field, there would be a contribution du phi. There's also the square of the Bondi news, which tells us how much gravitational radiation is passing through scribe plus. That's the term that you're used to. But if you look at the constraint equations, there's another very interesting term that doesn't get talked about quite as much. You have a plus 1/8, and then you have du, and then you have dz squared, czz, plus dz bar squared, cz bar z bar. And if we take this equation and we integrate it over the sphere, we get that the change of the total Bondi mass, not the local energy, but the total retarded energy at a function of u, is just equal to minus TUU. Because this term is a total derivative and does not contribute to the total energy. And that's the famous result. Since the stress energy is positive, that's the famous result that the Bondi mass always decreases. On the other hand, I'm interested in this term. I don't want to integrate over z. Sorry, this would be the integral d squared z of TUU, the total flux. On the other hand, let me take this equation and fix z and z bar, but integrate over all of scribe plus. Then I get the change in the Bondi mass, and let me put a little Bondi mass aspect as a function of z and z bar. I'm putting a little plus on it because I'm talking about scribe plus, is equal to minus the integral of TUU plus an eighth the integral of du of dz squared czz plus complex conjugate. This is a kind of funny term. It's a soft graviton. It's a zero mode. It's a soft graviton contribution to the total energy radiated through scribe plus, right? Because it's linear in the gravitational field, unlike this term, which is quadratic and represents the real radiation. It can be thought of as a soft graviton contribution to the local energy at an angle. And now, so this is the total energy radiated out through the angle z and z bar. Now, of course, MB plus, that is This is the change. So I want to consider situations where we decay through the vacuum, so the bonding mass aspect is the same up here as it is down here, but it's also the same here as it is over here. And therefore, it's trivial that this is equal to delta MB minus. So the change, so when you include this weird contribution, there is energy conservation at every angle. Okay, so the next thing we want to do is write down so we constructed the generators, the canonical generators of these supertranslation symmetries. And they are T plus of F. So this is something which, via Dirac brackets in the classical theory or quantum commutators in the quantum theory, generate these supertranslations. They're equal to the integral for scribe plus, it's scribe plus minus, d squared z f of z bar times the bonding mass aspect. And there's some 1 over 4 pi g here. And we see that if f is a constant, this is just the total energy. It's the Hamiltonian. But now I'm weighting that by a function which can vary over the sphere. And I can use the constraints. This is very similar to what I was writing just a moment ago, to write this as an integral over scribe plus du d squared z of TUU, the Radiev modes, and then plus a second term, which I'll call F plus, where F plus is equal to 1/8 the integral d squared z du f times du of dz squared czz plus the Hermitian conjugate. So F is linear in the graviton field. And so it creates a zero momentum soft graviton. So this generator has two kinds of terms, one of which generates. So we showed that T plus of F with all the fields, in particular CZZ, well, let me just write all the fields here, phi, generates the supertranslations on phi. And that was actually, I can't go into it now, but that was actually quite a non-trivial story. It involved keeping some very careful track of what happened on the boundaries of scribe plus. And an interesting factor of 2 coming from some constraints at the boundaries. And actually, the previous expressions in the literature didn't have it quite right. But anyway, after some long study, it all works, and it generates super translations. Yeah.
That's some matter, right? Does it have to be massless?
Yes, it has to be massless because otherwise it doesn't make it describe. And there should be some generalization of this to include massive matter, and of course Weinberg's theorem doesn't care. But you know, I have my hands full. In which case? Yeah. In electrodynamics, well, in non-abelian gauge theories, if you have non-abelian Coulomb phase, then you've already got it. But in electrodynamics, you would need massless charges, right? Otherwise, the whole story. Otherwise, everything cuts into superselection sectors, and it's just an uninteresting story. Okay, so now what? So now I want to derive a ward identity. So the claim is that since T plus and T minus are both written as boundary integrals and they're manifestly equal at spatial infinity, it should be the case that T plus S minus ST minus is equal to 0, where S is the S matrix. And this is the quantum version of the symmetry of classical gravitational scattering that I mentioned a few minutes ago. How does that work? Well, let's suppose we want to act with T minus on some incoming state. And I want to label my incoming states not by momentum, but by the point Z in which they enter the sphere. So I have some incoming state, Z1 in, Z2 in, and they have energies E1 in, so on. What is this equal to? Well, this first term, the radiative stress tensor, just gives me translations of these, so it just gives me a factor of the energy. But since I've got, there should be an F in there. There should be an F up there. So this gives me a sum. So that term will translate each incoming particle and give me an F of zk, z bar k, sorry, zk, z in k, z bar in k, multiplied by the energy that that particular particle is carrying in. And then that's just some number which is acting on this initial state. And the second term just takes plus, it just takes the initial state and adds to it a soft graviton. And obviously, there's a similar formula I can write for the out states. So now I just want to take the matrix element of this formula, which an operator relation. I want to take it between any two states. So let me write Z1 out, Z2 out, dot, 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 T plus S minus ST minus, Z1 in, dot, dot, dot. And this has to equal 0 because I've inserted 0. And I get two terms. I get that it's the sum of F of Z K in, Z bar K in, E in K, minus, so this is the sum for all ingoing and outgoing particles, F at Z out K, Z bar out K, E out K, all times the amplitude to go from whatever my in state was to whatever my out state was. And then I get a second term, which is Z1 in, Z1 out, dot, dot, dot. And then I have F plus S minus SF minus, Z1, where this is this operator which creates a soft graviton, Z1 in, dot, dot, dot. OK. So I've just derived, as a ward identity of BMS symmetry, a relationship which relates any amplitude to multiplied by some, you give me any function f. I have one such relationship for every function on the sphere. Take any amplitude multiply it by this weird number, and it's equal to the same amplitude with a insertion of a soft graviton. So okay, so now it's quite a few pages to show that this is Weinberg's soft graviton theorem in the way that he wrote it in momentum space. But if there were two such relationships on S matrix elements, we'd have a problem. So in fact, that's exactly what is. I'm done. That's it. Okay.
So, Eddie, I'm going to ask you the same question I've asked before because I still don't understand this energy conservation at every angle. So if I have counter-propagating beams of gravitons coming in at each other along the z-axis and they scatter out along the x-axis, it would seem to a naive person like me that energy has not been conserved at every angle.
That's because you're only including in your definition of energy just the TUU term, not the F plus term, not the soft graviton term. And it certainly wouldn't be true.
So what's really the case? If I send in two beams of gravitons towards each other along the z-axis, the energy is basically zero except along the north and south pole, right?
No.
Why not?
Because I mean, it's like saying, you can't avoid. The constraints tell you cannot avoid the production of these. I mean, it's like you can't send in an electron and not have a Coulomb field. You have to produce this, and so you have to produce it, and there it is. It doesn't change. These soft gravitons always have zero energy, of course. They're soft gravitons, but they will redistribute energy along the sphere. And now, you want to ask me, what is the physical consequence of this? What does this mean? Is this just some weird, of course, this isn't a weird definition of the mass. It's Bondi's definition that came a half a century ago, and it is what you would measure if you looked at curvatures of orbits of, you would measure the local thing. But if you adopt that definition, that it obeys this. But if you want to ask what the consequence is for scattering experiments, the consequence is the soft graviton theorem. The consequence, because you don't work in eigenstates. When we set up amplitudes, we don't work in eigenstates of the energy at every angle. We work in eigenstates of the total energy, but not at every angle.
Okay.
We have a picture of two scattering. I send in two gravitons and they scatter.
They produce another one.
No, but of course that is not what happens. If you try to do that, you will inevitably produce a lot of soft gravitons.
Yeah.
And so the physical content of it is precisely this relationship, between amplitudes with and without extra soft gravitons.
Okay, looks like Lenny has a question, but I don't know if you need a mic.
I don't have a question.
He doesn't need a mic.
I wanted to just sort of clarify. If we were doing electrodynamics and two particles, charged particles scattered and went off at right angles, probably most sensible people would have said that the charge...
Microphone.
Oh, okay, I'm sorry. If we were talking about electrodynamics and two charged particles came and scattered at 90 degrees, normally we wouldn't say that the charge was conserved at every angle. But you're just saying that you can count the photons that are going off, you can count the radiated Coulomb field that goes off, and think of it as part of the charge.
We don't usually talk about local charge in electrodynamics.
Right. Basically, this is coming from del dot E equals rho.
Yes.
And saying that a new definition of total charge is del dot E.
No, I'm not giving any new definition of total charge.
I know.
And the definition of local charge...
local charge is the same, but...
local...
Gauge generator.
When I say local charge, I don't mean the local charge current.
I know.
I don't mean J. And when I say local energy here, I don't mean TUU.
No, I think you mean the generator of the gauge transformation.
I mean the generator of the gauge transformation.
Right.
And for electromagnetism, that would simply be the electric field, the radial component of the electric field,
right,
which can be measured at every angle.
Right. Plus the real charge. Plus the ordinary charge.
No.
No? Oh.
The charge is, if you want to ask how that measure, how the radial component of the electric field changes as you move along scribe plus, that will involve the current. That will involve the current going through scribe.
Yeah.
So when you say that, the total electric charge is given by the electric field, you don't say you have to add to that the actual charge of the matter.
No.
Yeah.
Okay. Other question? Oh, question over here.
Just to sharpen what Greg said, suppose that I send in two gravitons with energy E, and I make a measurement. Of course, I have to allow for solid gravitons, but suppose that I make a measurement and I measure two gravitons coming out at right angle, and they have energy E minus delta E. Right? So it means that whatever energy you emitted at all other angles is at most twice delta E. So it doesn't seem to be enough. So are you saying that this process is just impossible?
The soft graviton energy doesn't have to be locally positive. In fact, it always integrates to zero. It's a total derivative.
Question back there. Oh, Steve. Okay, I didn't see you.
But the matrix element of the statement that energy is conserved of the conservation law is the soft graviton theorem.
So
Steve?
In this case where you're, say, scattering, if you have beams coming in from opposite directions, so you have sort of the energy of the beam coming in, but I guess, are you saying that you have a contribution that you see in your surface term, sort of in the other directions that corresponds to the basically the Coulomb field of the...
You can't just send in some radiogravitons. The constraints don't allow you to do that. Right?
You can send in a beam of, say, particles coming from opposite directions. Why not gravitons?
That's like saying you can send in an electron without sending any in any electromagnetic fields. It
there's it carries with it a gravitational field, and that's okay, and that's what you're saying that makes an important contribution.
Field that redistributes the energy and makes it conserved at every angle.
Right. Okay.
Okay. More questions, or perhaps we go to lunch. Okay. Let's thank the speaker again.